So here, the null A is a subspace. R. Basically doing this theorem here so that we can review what does it mean to be a subspace. Well, let's see, why is it true? Can anybody remind me, what are kind of the three big things we need for something to be a subspace? What properties do they have to have?
The zero vectors in it?
Zero vector's got to live in that. Let's check that first. Next, the vector full of zeros, then AX is the same thing as A0, which is 0. Check window, no problem, got that. Okay, what else? Yeah,
You have to be able to add two vectors and have it still be in the subspace.
that's right. If you have two vectors that live in the subspace, when you add them up, it's still gonna be in the subspace. So suppose U and V live in the subspace. What does that mean? Well, that means that that's the price of membership, baby. What these properties, or what it has to happen for these two to live in the null space is A times U is 0 and A times V is 0, right? So let's conveniently add these up. Right? And if I wanted to feel like I was really smart or something, what could I do? I pull out that. So U plus V is N all the way. So I've got my second thing checked out. Finally, oh yeah, what is yeah. Right, if you have a vector that lives in your subspace, when you multiply it by some number, it's got to still be in there. So let U be a null A and lambda some real number. We need to show that when you multiply U times its number, it still lives in the subspace, right? Well, this right here means that AU is 0. So I can multiply both sides of that equation by lambda, can I? And you know what? I don't know much, but I know when I hit a vector full of zeros with a number, I get a vector full of zeros. And I can pull a little bit of mathematical prestidigitation by sliding that. So lambda U is in null A. And big smile, we got them all. So it is indeed. Okay, any questions so far? Okay. Here's another kind of brain tickler to add to your repertoire here. Suppose you have an M by N matrix. We know that the column space is a subspace of RM, right? Because the span, it's the span of the column, so we've already shown that the span of any collection of vectors is always a subspace of where the vector live. When is the column space the whole shebang?
Never.
Okay. There, well. If and only if the equation AX equals B can be solved. Or is consistent for all B and Rn. And this is true if and only if. I like the practical answer I got here. If and only if there's a pivot in every row. Y'all remember that one? If there's a pivot in every row, this is good to go. This will come up, I think, as sort of a kind of a side note on the exam. So let's go back. Actually, if you look at the way your book talks about things, they talk about basics in the next or in the next section, and we'll do that too. We already know what a basis is for Rn, right? Oh, maybe we do. Somebody remind me, what does it mean for a collection of vectors to be a basis?
They span the whole space.
They span whatever space they're in, right? And what else?
They're independent.
They have to be linearly independent. So in a certain sense, that linear independence, that's sort of an efficiency condition. There's lots of ways that you can span. So for example, if I wanted to span R2, the plane, do you know what a lazy person like me might do? I might say, you know, that's spanned by every single vector in R2, right? I could certainly do that, right? But that's really not efficient, right? Because that's a lot of vectors. That's infinitely many vectors. But I can more efficiently say, you know what? I only need two vectors to span all of R2. I only need two coordinates to specify where I am in a plane. And I might pick 1, 0 and 0, 1, right? That set is linearly independent and it spans R2. And it sort of maximizes efficiency because all you need is two instead of a lot of them. So let's go through and make sure we know how to do this. And this might help some of you. There were some subtle things that went wrong for you on the exam. So let's kind of go through this carefully. Let's let A see, what do I want to do here? 3, 2, 1. 2 minus 6, 11. Bigger than 3, 1 minus 1, 0 minus 1, 3, and 4, 1 and minus 3, 5. Okay, so let's suppose I have this matrix here. Notice this matrix is 3 by 6, right? Okay. This is an important thing that you need to take away from this class. So make sure that we do this right. Okay, I want to find a basis for null in the column. By the way, see, this is one of the great things in math about checking yourself. What do you expect to get? Right. So think about this kind of size wise. What do you expect to get? For null A, what's the dimension of null A? So null A should be an R6, right? So I expect it to be 6-dimensional vectors. column A lives in R3, so I expect to get 3, so that's kind of a gut check for me. Okay, guess what? You know, it's almost like I'm having flashbacks here. Guess what we're going to do? Row reduce, right? So let's do that. I want to take this thing just up to the top and take all your ones, right? I'm gonna put that up top. I'm gonna multiply this by -3 and make it the second row, okay? So that's going to be 0, -1, -2, -1. I'll make it 3. So that's gonna be 9 minus 6 is 3. -15 plus 11 is -4. Everybody okay with that? I'm gonna multiply this by -3 and make this the last row, the third row. When we get 0, -2, -4, -3, 8, and -12. Okey-dokey so far? Okay, again, I'm gonna do a couple steps here. Okay, the first thing I did is I just changed the sign of that middle row, right? Because I ultimately I'm only one here. What happens when I add this up here? I'm going to get 1, 0, -1, 0, 0, 1. And I'm gonna multiply this by -2 and take this out. So it's gonna be 0, 0, another 0, that's my lucky day, -1, what's about -2, and -4. And finally, what I'm gonna do is I am going to, I think this will be my last step here. And this matrix slide will be useful for me moving forward. I'm gonna leave the top alone. I'm gonna change the sign at the bottom, so it's proper rubber echelon form. And to get the middle row, I'm going to just straight up add here. So I get 0, 1, 2, 0, -1, 0. Okay, get that right. Okay. Any questions on that? Okay. All right, I'm all proud of myself because I've put this in rubber discussion on form, but now what?
Trying to do a system of equations.
Yeah, so let's go for the null space first. So let's look at this as a system of equations here. If I do so, what are my basic variables here? I agree. The basic variables correspond to column 1, 2, and 4. And of course, what's left over, the non-pivot column should be 3. In our case, it should be 3, 5, 6. Well, let's write these equations. And see, this is a good gut check. So a mistake that a lot of people made, which isn't really a mistake, you can get around it, but it makes your life, don't do this because it makes your life much more difficult. Some people on some of the matrices actually bailed before you got to the final row reduced echelon form. So instead of like going all the way to here, see how you've got ones in the pivots and you got zeros for the rest of the column here? You might have stopped here, right? Where these two pivots are good and this one has something else in the column. What that's gonna do is that's going to tangle in your free variables and your own. What you got is not wrong, but when you want to write it in one of these vector forms, you've got to untangle it again. So please go all the way when you're trying to do consistent equations, all the way to row reduced echelon form, because when you write the equations down in this form, there's going to be stuff. So for example, this right here is a basic variable, right? Because it's in a pivot column. And this equation here will be a basic variable in terms of another basic variable. And so you've got to untangle that, and it's a mess. So if you get to row reduced echelon form, you're never going to encounter this problem. So let's see what the equations say. And this is a good gut check on checking yourself. Do I have something that makes sense here? The first equation is x1 minus x3 plus x6 is 0. The second equation is x2 plus 2x3 right, I was looking wrong there. Here we go. 2x3 minus x5 is equal to 0. And finally, the last equation is x4 minus 2x5 plus 4x6 equals 0. Right? Everybody okay with that? Now, at this point, here's a good gut check that you're making good progress and things are going as they should. Write your basic variables down in terms of the other ones. X1 is x3 minus x6. X2 is minus 2x3 plus x5. And x4 is 2x5 minus 4x6. Right? The key that makes me know that I think I'm on the right path here is what's on the left side of all those are the basic variables. On the right side, I've got nothing but threes, right? 3, 5, and 6. That's it. Right? If you had used this equation here, for the equation that has x2 in it, you would also have an x4 over here, which also belongs over here, and you get a mess. Everybody okay with me? If you get to row reduced echelon form, you'll never have to worry about this. Okay, so let's get a basis for this. Well, so what is a typical a typical vector in null A looks like this. Equations are going to tell me what's what here. X1 is x3 minus x6. X2 is minus 2x3 plus x5. X3 is free, so it is what it is. Just got to write it down. X4 is 2x5 minus 4x6. X5 is free, and x6 is free. And there you go. Now, if I pull this apart, then I can get what I desire. And it should show up with your basis and your span, sort of. This is let's see, x3. So you should have one of these vectors for every free variable. In this case, x3, x5, x6. Can somebody tell me what the vector for x3 is?
1, -2, 1, 0, 0, 0.
Agreed. Everybody see how you got that? You're basically, there's a 1x3 here, a 2, a -2, and a 1, no x3's down. But x5 times what?
0, 2, 1, 0, 1, 0.
Okay. 0, 1, 0. 2, 1, 0. Finally, what's your vector for x6? -1, 0, 0. And then what? -4, 0, 1. What? Yes.
Oh, stretching, sorry.
Oh, no worries. So it's fairly easy to verify that these three vectors, in fact, because it's row A, right? And they span, and in fact, it even tells you how they span. Something times this one, something times this one, something times this one. Because x2, x3, and x5 are free, they can take on any kind of x5. So there's your basis for your null space. Everybody okay with that? Column space. You know how we can tell that one? Yeah.
The pivot columns, but from the original.
Ah, right. You gotta be careful about that, don't you? This has 3 pivot columns and they correspond to the basic variable, right? Here they are. The pivot columns are 1, 2, and 4, right? Now you gotta be careful and take 1, 2, and 4 out of the original matrix. So I'm gonna be careful. Three, 3, 1. Two, 1, 1. Two, 0, 1. Let me say something that's not obvious, but it's a consequence of our computation here. And that is those 3 vectors, 3, 3, 1, 2, 1, 1, and 2, 0, 1, they have to be linearly independent. It's not really clear just looking at them, is it? How can we check if they're linearly independent? You throw it in a matrix and see if you can row reduce it to the identity. If it's easy, you could take its determinant and see if it's non-zero. There's a number of things that we can do, right? But even though it's not obvious, these 3 are actually linearly independent. That's another gut check. You check and see this. Let me ask you this. And this happened to a number of you, and I was sympathetic, but I did take off points. What would happen if you wrote these vectors here as your basis?
It's just my identity matrix, yeah.
Well, that's right. And you would be correct in this example, right? Because, let me ask you this. What is the span of the column space of A?
R3.
It's all of R3. What's the span of those 3 vectors right there? All of R3. You would have actually gotten it right if you had picked the wrong vectors, but it's only because you got lucky, right? It is possible for us to have row reduced this matrix and gotten a row of zeros, right? And in that case, what would have happened is, well, in fact, you don't even have to get a row of zeros. You can also have other things go wrong. Matter of fact, so here, that's why you need to go back to the original matrix. You would have gotten lucky in this particular instance, but you can't count on that in general. What's the dimension of another gut check? What's the dimension of the null space?
6.
No, the dimension of the null space.
Oh.
Three, right? Cause I got three vectors. What's the dimension of the column space?
Three.
What's that add up to?
6.
How many columns in my matrix originally? Another good gut check, right? So you can always kind of check these things out, or at least get a feel for, you know, if you're right or not. Okay. Let me give you a definition, which you've seen before. We've gone over this, but I'm gonna do it in a more general sense than you've seen it. Actually, I have defined it in this sense, but I'm gonna give you some examples of it. Here's an example, or definition. Let B and W be vector spaces. When I gave you this definition earlier, I said let Rm and Rn, here, any vector spaces you want. A function, T, B to W, is a linear transformation if we gotta have a couple of things here. Have you all, the, you know, calculus commandos from your past life have encountered all kinds of functions. Most of them are not linear. What is it about a linear transformation that makes it linear?
The origin stays put.
Okay. I'm gonna put that as a 0. And that is actually, what else happens? What's true about that?
The
Spread that out like that. And 2. Some of these are very reminiscent of subspace, and there's a reason for that. It's a linear transformation if it basically behaves like a line through the origin. T of u plus v is T of u plus T of v, and T of uv is lambda du. Now, one of the things that we looked at earlier is we looked at linear transformations, and I sort of defaulted. How many of you looked over your exams and saw, I think the last question on the exam was something like, why is it true that T of u is equal to 0? Y'all remember that last question on the exam? And some people said, oh, write it as a matrix. And if I take a matrix and multiply by the 0 vector, I get 0, right? A lot of you did that. Anybody read the comment I put on that? I said, okay, for now, right? Because right back then, we thought of every linear transformation as a matrix. And it actually is true that every linear transformation between finite dimensional vector spaces, you can write as a matrix. But here's some linear transformations that aren't obviously a matrix. Although this first one is, until I go to all polynomials. So here's an example. Let P3 set of A plus bx squared plus bx cubed. A, B, C. These are all polynomials. This is 0 and all polynomials of degree 3 or less. For all polynomials that I could ever create just by using these building blocks, right? So x cubed is one of these things, x squared is one of these things, x cubed plus 10x squared minus x plus 43, that's one. Everything I can create, right? I'm gonna do this very informally, but this is a vector space, isn't it? What's the zero vector for this collection of polynomials? What's the well, in fact, A is zero, right? In fact, you have to take all A, B, C, and D to be zero. Just big back zero. You add that to any polynomial and it doesn't change it, right? That's your zero vector. What happens if you add two polynomials of degree 3 or less? What do you get?
Polynomial of degree 3 or less.
A polynomial of degree 3 or less, so it's closed under addition. What happens if I take a polynomial of degree 3 or less, something like this? What happens if I multiply this by lambda? The lambda just shoots all the way through and I've still got a polynomial of degree 3 or less. Everybody okay with that? So this is an honest to goodness, old fashioned American vector space, right? So I can think of the linear transformations. Input, polynomial degree or less. Output, it's derivative. What happens when you take a derivative of polynomial of degree 3 or less? What do you get? Polynomial of degree 3 or less for sure, right? Is this a linear transformation? Well, let's go through it and think carefully. What happens when you take the derivative of the zero vector? The zero vector in this case is a polynomial 0. What happens when you take derivative of 0? You get 0. What happens if I do this? What if I need to take the derivative of a sum of two polynomials? What happens? They probably beat this into your head in Calc 1, right? In fact, at the time, they might have even slipped and said, oh, taking derivatives is linear, right? And that's what it is. The derivative of the sum is the sum of derivatives, which is p. Okay, so it does that. Well, this is taking a derivative of lambda f of x. And what happens when you take the derivative of a constant times a function? You can pull a constant out, can't you? Derivative of 2 sine x is 2 cosine x, right? Everybody okay with that? The derivative is a linear transformation. Anybody know how to write this matrix? By the way, let me ask you this. If you have a polynomial of degree 3, so this question is going to come back to us in a moment. If you have a polynomial of degree 3, how many times do you have to take the derivative of it before you get to 0? I think that's right? Derivative, first derivative is down to degree 2. So just take x cubed. 3x squared, 6x, 6, 0. 4 derivatives is gone. Everybody agree with that? Agree. So anything out of here, 4 derivatives is gone. Let's see if we can make a matrix. By the way, can anybody guess what a basis for P3 is? What are you supposed to dimension is? Give me a basis. The clue is actually in here, the way you've written it down. You might think of a simple basis. Look at that.
Well, that's 4 columns and now.
Well, right, I go that way, but how about just in terms of polynomials? What are the simplest polynomials you can make that be a basis?
Think of a vector as like A, B, C, D, then they can just have effects, the E1, E2, E3.
How about that? 1, x squared, just the different powers of x, the 0 power, the 1 power, the 2 power, and the 3 power. Notice this set spans because anything in P3 is a linear combination of that, right? And if I have a polynomial, suppose I have a polynomial a plus bx plus cx squared plus dx cubed, if that polynomial is always 0, no matter what you plug in for x, that means a, b, c, and d always have to be 0. And so it's linearly independent. So this is a basis, right? What's your, and it's got 4 elements in it, right? What's your favorite basis of R4? What's everybody's easiest basis of R4? Yeah, the heaves, right? Y'all see kind of the rationale? Every time you go down, you kick up the power base by 1. Right? Let's see what matrix we should build. So this is actually, we're kind of going for an idea that we're gonna, kind of a big idea we'll come up with later. If I take the derivative of 1, I get 0. Everybody agree with that? What happens when I take the derivative of x? What do I get? 1. What happens when I take the derivative of x squared? What do I get? 2x. When I take the derivative of x cubed, what do I get? X squared. Am I okay with that? So let's think about this in terms of our new basis. This basis was 1, 0, 0, 0, and that should go to 0. Right? X was 0, 1, 0, 0. And its derivative goes to 1. And in terms of our basis, what was that? 1, 0, 0, 0. Everybody okay with it? How about this one? X squared. That's 0, 0, 1, 0. Where should that go?
0, 2, 0.
0, 2, 0, 0. Because you need 2 x's, right? This one's x. Everybody okay with it? How about the last one? Let's put it over here. What should that go to?
0, 0, 3, 0.
I agree. Let's make the matrix. Y'all remember that to make a linear transformation, to make its matrix, you just look at the effect on the basis and put the columns in order, right? So the matrix for differentiation should be the first basis gave me 0, 0, 0, 0. I got 0, then I got 1, 0, 0, 0, 0, 2, 0, 0, 0, 0, 3, 0. Everybody okay with that? What happens if I square this matrix? By the way, before I do that, you can actually test this because if you have A, B, C, D, this goes to B, 2C, 3D, 0. Agreed? Translation, d dx, that's what this thing's doing, of the polynomial a plus bx plus cx squared plus dx cubed is equal to b plus 2cx plus 3bx squared. That's this vector read off, and that's exactly what you should get. Everybody see that? What's in square? What happens when you multiply this by itself? I get 0, 0, right across the perfect 0, 0, 2, 0, 0, 0, 0, 6, and the rest are zeros. You can check, but this is taking the derivative twice. Do this again. 0, is that right? Right, so if you, oh, I've got to do it by n. 0, 0, 0, 6. And that's right, isn't it? Yeah. That's taking the derivative 3 times. And what did you all tell me happened when you take 4 derivatives of this? 0. If you multiply it one more time, you get the matrix of all zeros. So now, basically, I have turned, taking the derivative into a simple matrix operation, right? That's really kind of cool. Let me give you another example. I'm going to give you a couple of examples to take home and think about. Consider all solutions to the differential equation y double prime of y zero. How many of you have ever seen this equation before? This is a differential equation, and what it means is I have an unknown function called y equals f of x. And I don't know much, but I do know that when I take the second derivative of this function and add it to the function itself, I get 0. So in other words, if I take the derivative twice, it's basically like changing the sign function. One function that satisfies this is 0. Right? This is actually the collection of all of these. This is vector space. Anybody know another solution? Cosine x is a solution. So is sine x. And in fact, you should check, this is actually a vector space. So is any linear combination of sine and cosine, including 0. Okay. Any questions? Any questions? All right, look this stuff over, do the homework, let me know if you got any problems, and other than that, I'll see you guys on Wednesday. I'll have to prove the short.